In the mission to explore the mysterious expanse of space, humans have designed and fired off a great number of rockets and satellites. Satellites function in Earth's orbit until they no longer work and remain in the atmosphere as waste. Whilst one of the techniques that rockets use to reach farther out into space is the release of certain parts of the rocket that serves no further purpose, namely the propulsion system. Not only does this technique reduce the mass of the spacecraft, it also pushes the spacecraft further into space by dint of Newton's third law. Every action has its equal and opposite reaction. But this begs the question, what happens to the machines we leave behind just floating in space? What happens to the systems we send out after? This is the question of how can we solve the problem of space junk.
Well, the debris we leave behind that sits within low Earth orbit is classified as space junk. Objects in low Earth orbit have an altitude of 2,000 kilometers or less and orbit the Earth approximately once every 2 hours.
Space junk consists largely of human-made objects, such as pieces or parts of spacecraft, or satellites that are no longer working, or even tiny specks of paint. All space junk, even the ones that seem harmless, are extremely dangerous due to the rapid speeds at which objects in space move. Space junk is often moving at speeds upwards of 24,000 kilometers per hour, almost 7 times the speed of a bullet. This means that even tiny, seemingly harmless objects can pose a huge threat of collision due to their high kinetic energy, as has been seen by the National Aeronautics and Space Administration, NASA, who has stated they are required to change their space station windows due to damage caused by only small fragments of paint. As astronauts in the International Space Station who frequently need to steer the station to dodge these particles and patch up holes created by collisions, making it an extremely important issue.
Space junk is not only an issue for our current satellites, as it also poses a challenge to any future space missions we may want to make. If we fail to account for space junk when launching new spacecraft, we may face the consequences of collisions. In the best case, collisions leave only minor abrasions, whereas in worse cases, they can damage spacecraft to such an extent that they limit or even destroy the spacecraft's operational capabilities. This results in more space junk and debris in orbit. This then results in higher chance of space junk colliding with existing satellites due to the increase in debris from the failed spacecraft launch. This effect is known as the Kessler syndrome, a phenomenon described in the 1970s by NASA scientist Donald Kessler. If we do not address this issue soon, space junk could become an irreversible problem, making future space exploration and investigation virtually impossible. Fortunately, it's not too late, and we still have a chance to fix this problem. Several investigations have been conducted to assess the effectiveness and feasibility of various proposed solutions.
One proposed solution is called laser irradiation. This method involves using high-energy lasers to melt debris into smaller pieces. This debris typically then plummets back to Earth and is burnt up in the atmosphere. Although this method is efficient and precise, it requires a lot of energy as we are transferring energy through light. This could make this method extremely costly despite its efficiency. Using a large laser necessitates significant energy consumption, one that many governments don't have the resources or incentives to do so. Such technology hinges on development of cost-effective and efficient sustainable energy, but also, more importantly, it doesn't work for large debris.
Alternatively, instead of eliminating debris, we can look to mitigate the formation of more space junk in future research expeditions. Choosing materials with high toughness or durability reduces the likelihood of spacecraft components becoming debris due to collisions with micrometeoroids or other objects in space. Self-healing polymers and shape memory alloys both autonomously return to their original shape after deformation, and lightweight metal foams can absorb large amounts of kinetic energy. By using these materials, we can reduce the use of metallic materials such as titanium and aluminium, and therefore minimize fragmentation during collision. For satellites with an expected working life, we can install propulsion systems that actively reduce orbital height once the satellites have gathered enough information. This means that when satellites are nearing inoperation, we can maneuver them back into the atmosphere to be burned up, reducing the time they spend acting as potential debris in space.
Space junk has been a rising topic of concern, specifically for the increased risk of collision, and may become an irreparable problem if we ignore it for any longer, potentially inhibiting us from traveling outside of Earth due to the layer of space junk covering our Earth's atmosphere. The fast speeds and increasing number of debris is becoming a greater and greater issue. By carefully selecting materials and accounting for any space junk that our spacecraft may leave in orbit, we can minimize the impact of any potential debris on our ventures into space.